Okay, the definition of the derivative. At a point. Right. The formula you've seen so many times in your book looks like this. The derivative at a number a is equal to the limit as h approaches 0 of the difference quotient. Alright, by now we've worked with this difference quotient a lot. What may be unfamiliar at this point is that we're no longer letting a be a particular number, but we're thinking of a as just a variable. A can be anything at once. And so at the end of this, we're going to arrive at a formula that involves a. An alternative definition, which is sometimes used, though we'll make very little use of it. We've seen this form of the difference quotient also. But we're primarily going to focus on this first definition. Right. Now, what will change in a moment is that we want to consider not just a number a, but any number x. So all we're going to do is take the number a here and replace it with x in our definition. If that makes you uncomfortable, you can continue to use a, and then when you're all done, you replace it with x. So if we did that, we would have f prime of x it's just because our ideas about the derivative are going to shift a little bit from just being a simple formula to where the derivative is a function that we derive from the original function. Right, and that function tells us certain things. For instance, it tells us the slope of the tangent line at a particular value of x. And switching the a's to x's helps make that transition to thinking about the derivative as a function. All right, let's look at a couple examples of these computations. In particular, we're going to look at 3 examples. Okay, we're going to look at finding the derivative from the definition for a simple polynomial, finding the derivative from the definition for a function involving a square root, and finding the derivative from the definition for a simple rational function. Now we can of course do many other things with other functions, and some of those investigations will happen in later chapters. All right, so let's move on to our first example, working with a polynomial. Okay, so for the polynomial, we're just going to use a simple quadratic here to illustrate. Calculate the derivative using the definition at a number x, or at a number a. The computation is exactly the same. All right, I'm going to work it in terms of x, because as we go forward, we're going to use x more often than a. We write in our definition. And at this point, I'm not specifying a particular number for x, or if you'd rather, for a. Okay, I'm just going to work out what the formula is going to be that defines this new function called the derivative. First, I set up my difference quotient. I evaluate my function at x plus h. Since my function takes 3 times my number squared minus 5 times my number, I get here 3 times my number squared minus 5 times my number. I like to use lots of parentheses here to remind me about minus signs. This minus sign in particular in the middle of the difference quotient is one that often gets fouls things up if you aren't careful. Now I subtract the value of the function evaluated at x. And maybe you can see here where that minus sign from the center of the difference quotient could be a problem if I failed to distribute it. Now we're going to expand things. Remember, expanding is one of the 4 main algebra tricks we have for working with difference quotients. The 4 main algebra tricks were factor and cancel. Let's write them up here. not just working with difference coefficients, but working with any kind of indeterminate form of a limit. Expanding is what we're going to do here, and then we'll do a little factoring and canceling. Common denominator, we're going to need that when we go to deal with rational functions. And conjugates, which we're going to need when we deal with square roots. So here I'm going to expand. Being careful with minus signs and distributing constants. Minus minus is plus 5x. Now if I've been very careful, I'll get a lot of cancellation at this point. Now here I have 3x squared and minus 3x squared. Right. When I cross out the 3x squared here, I don't want to cross out the 3. That still needs to be distributed onto these other terms. But I am going to cross off this x squared because that represents 3x squared. Now we'll go ahead and distribute the 3 and clean everything up. 3, 6xh. Right. Now if you're being good, what has to happen here at some point is that I can cancel out the problem. Right, and the problem is that the h in the denominator is going to 0 at the same time the numerator here is going to 0. But I can factor away that problem here. Now we cancel out the common factor of h. Now we are in a position to use direct substitution. Right, I no longer have an indeterminate form. I'm no longer dividing by 0, so as I let h go to 0, I don't need the limit symbol anymore. So, in fact, our derivative is 6x minus 5. Right. So if I wanted to know the slope of the tangent line to the graph of f of x at a particular value of x, say at x equals 2, right, this is just a side calculation here, then the slope of that tangent line would be f prime at 2, or 6 times 2 minus 5. I can just use my derivative formula now. Alright, so that's one reason why we would like to have that formula. Now if I want the slope at a different point, I just use the formula. I don't have to repeat the entire calculation. So that's an example of using finding the derivative from the definition for a polynomial function. Let's try a function involving square roots. I'm just going to make one up here. Let's say the square root of 3x minus 5. I seem to be fond of 3's and 5's at the moment. At the definition of the derivative at a number x or at a number a, an unspecified value, if you're having troubles thinking about using x's as the variable instead of a, you can work with a, but it would be more useful if you can learn to work with x as we go forward here, because that's what we're going to do as we move ahead. So my function takes 3 times my number minus 5 and then takes the square root of that. So 3 times my number minus 5 square root. So I evaluated x plus h minus the value at x, all divided by h. Alright, and as always I've got an indeterminate form here. As h goes to 0, we have 0 upstairs, we have 0 downstairs, 0 over 0, doesn't mean anything. We have to find a way to cancel out this h downstairs. When we have square roots, we want to multiply by the conjugate very often, and that'll help us get rid of this indeterminate form. So we're going to multiply by the conjugate of the numerator. this line will look long. Along the way there, I'm going to go ahead and distribute that 3. As you practice multiplying by the conjugate, it's often something you can just you can often skip the step of writing it down and jump to the conclusion. I won't do that here, to be clear. And the denominator is identical, all right, because we're multiplying by the quantity 1. Now hopefully this algebra is familiar. I've got a minus b times a plus b. When I multiply that out, I get a squared minus b squared. You can also check that by FOILing. When I take the square root times the square root, I get the quantity underneath the square root. So 3x plus 3h minus 5. I like lots of parentheses here. Minus a squared minus b squared, so 3x minus 5. Right, we're using lots of parentheses because we need to make sure that minus sign there gets taken care of. And then downstairs, don't expand anything yet. Upstairs, 3x minus 3x, those are gone. Minus 5 minus minus 5, those are gone. All right, you may notice that what remains here is 3h. We're dividing by h, so those h's will cancel. Right, so now I can get rid of that h with this h. All right. Because it's now a common factor in the denominator. It's very important that this is now a plus downstairs after multiplying by the conjugate. And I have an error here. Should be 3h, it's that second term. Now we can use direct substitution. We no longer are dividing by 0 as h goes to 0. So we direct substitute. 0 for h. And I get 3 over the square root of 3x minus 5. But now there are 2 of those, so we need a 2 here. So that's our derivation of the derivative for a square root function. All right, one more example, something involving a rational function. We'll keep it fairly simple. Okay, and again, we're not going to specify the point we're interested in before we compute this derivative quantity. All right, we'll specify that after, so maybe we could check multiple values of x or a. All right, it doesn't really matter. How about 7 over 2x plus 5? I know you can't quite see the 7 that got off the screen there. 7. So forming the difference quotient. I'll write it out. Tempted to be lazy and not write it out, but I want this video to be very clear so you can follow along. So I evaluate the function x plus h. So 7 over 2 times my number plus 5 minus the function evaluated at x. Particularly when I'm working with fractions, with rational functions. Right now I have fractions within fractions. I find it helpful to take this h in the denominator here and move it out front as 1 over h. Multiplying by 1 over h is the same as dividing by h. Now we're going to rely on the common denominator trick. Our 4 tricks: factor and cancel, expand, common denominator, and conjugate. Here we need a common denominator. Right? We're dividing by 0 here. As h goes to 0 here, these two quantities are the same. Right? So I have a 0 in the numerator. So this is indeterminate form. I need one of my tricks for indeterminate forms. Fractions suggest that we do common denominator. So we're going to multiply 2x plus 5 over 2x plus 5. And that guy, so we're going to get 7 times 2x plus 5 minus 7 times and then I need the whole denominator. Again, I'm not going to expand down here until I need to. My goal is to cancel out this h here. I'm going to have to cancel it with something up here. So I'm going to focus my attention on the numerator. I need to find an h up here that will cancel. I can't just cancel an h because I see an h. I have to make sure that I have a common factor of h to cancel out this h. I'm not going to focus any attention down here until later if I need to, because once I cancel out that h, I can merely evaluate by direct substitution. This h here isn't going to present us any difficulties whatsoever. So don't expand, that's a waste of energy. Don't expand the denominator. The numerator is a different story. The 7 here, 7 is in common to both, so why don't we just factor it out and leave it out front. So then I have 2x minus 2x, 5 minus 5, but I've forgotten a term here, minus 2h. Alright, so now I found the h as a common factor. Now this is the only term in the numerator. Just to be very clear, let me write it out again. In the numerator here, I have minus 14h after multiplying the 7 times the minus 2 over h times 1 over okay, we switch some things around and switch their locations, but hopefully that's not a problem. Right? A fraction times a fraction, I multiply the numerators so I can associate these quantities however I like. Minus 14h times 1, or 1 times minus 14h, or 7 times minus 2, whatever. Alright, now as h goes to 0, after canceling out that h, I'm in a position to use direct substitution. This minus 14 is still here. This h is going to 0. And finally, we're left with minus 14. Downstairs, 2x plus 5, this h has gone to 0, times 2x plus 5, or 2x plus 5 squared.